Morning, guys. Today we're going to learn more about drawing ray diagrams. So we're going to do some more with curved mirrors today, and then we're going to get into thin lenses. So we'll start off with curved mirrors. Here we go. Here's a curved mirror. And last time we did ray diagrams where the objects were farther away from the center than the mirror was. Today we're going to look at ones where we have the object between the focal point and the center, or between the focal point and the mirror, and we'll see what happens with that. Okay, so let's start off with one here where we have the um, object between the mirror and the focal point. So we'll put one right about here. This will be a good object for us. Okay, now we use the same rays that we did last time. There's nothing different about that. So one of the rays was a ray that passed through the center and then through our object, and then it would bounce straight off the mirror and come back through the center again. Because remember, this is the center of the circle that makes up the mirror, the spherical mirror. So any ray that comes from the center will hit the mirror perpendicular and bounce right back the way it came. So we're going to put arrows on both directions here to show this is a ray coming in from outside, bouncing straight off the mirror, going back the way it came. Now the next one was a ray that passes through the focal point and then through the object and then hits the mirror. And as you recall, a ray that does this will come out parallel to the principal axis. So we'll draw that one carefully. There we go. So that one goes this way. Because remember, this is just the reverse of a ray that comes in parallel to the principal axis. Then it will bounce off the mirror and pass through the focal point. So we're just doing that in reverse. And we're starting with a ray that comes from the focal point and it's going to go straight out from the mirror parallel to the principal axis. And then the third one is a ray that comes in parallel to the principal axis and passes through our object. And then that one will reflect back through the focal point. Okay, and come out this way. So we might be saying, okay, well, none of these things seem to be coming from any point other than the focal point itself, and those rays are all going toward the mirror and then coming out. So they seem to be diverging from the mirror. And that's true. But if we then project these rays back through the mirror, it appears to an observer that they are all coming from some point behind the mirror. So this is very similar to the bathroom mirror situation that we had last time with the plane mirror, the flat mirror. The image appears behind the mirror. It appears to us as we're standing here and looking at this that the image is behind the mirror. The light rays appear to be emanating from this point in space because of the way they reflect off the curved mirror. So this was the object, this is the image, and this is another situation where the light rays do not actually pass through the image. The light rays bounce off the mirror and come out. They only appear to be coming through the image, but no light actually passes through this point in space. So that means this is a virtual image. And in this case, it happens to be magnified. So if the object is between the focal point and the mirror, then the image appears behind the mirror. It's a virtual image, but it is magnified. And this is how makeup mirrors or magnifying mirrors work. The image is upright. You can see yourself back there, but you look bigger than you are in real life. So you can see some detail while you're trimming your nose hairs or doing your eyelashes or something like that. Okay, so that is a ray diagram for the object between the focal length and the mirror. Now let's do one more of these where we put the object between the center and the focal point, and we'll see how this one works. And I would like you to pause the video here and see if you can do this on your own. If you get stuck, then you can start it up again, but see if you can do this one entirely on your own. All right, let's see. I'm going to make this a little bit smaller so that our rays will work. We use the same rays again. We have one ray from the center through the object, which will come straight back down through the center. So that's one. We have another ray, which is comes through the object, through the focal point, and that one will come out parallel to the principal axis. And then we have a third one that comes in parallel to the principal axis and reflects out through the focal point. And as we can see, all of the rays converge at this point, all three. Now remember, the base of the object, for convenience, we put that on the principal axis so that we can see how it works. And all of those rays will come right back out through the principal axis when we do that. So we know the base of the image is still on the principal axis, and the top is now pointing downwards. So in this case, the image has been flipped upside down, and all of the rays seem to be coming through this point in space. So this is a real image, and it happens to be upside down. We call that inverted, but it makes a flipped image, but it's a real image. And notice in this case also it's magnified a little bit. It actually gets a little bit bigger. So it's another magnification, but it's upside down. So we don't usually do makeup mirrors like this one, because then the image that we're working with is flipped over, and that's just confusing for us. Anyway, so that's a curved mirror. So yeah, curved mirrors do different things depending on where the object is. If it's outside, the image appears inside, and well, anyway, yes, that's curved mirror. All right, now let's go to thin lenses. Now, before we get to this, I need to tell you a little bit about lenses. Let's straighten that out here while we're here. Okay, let's reduce that a bit, and we'll go to this. Okay, you remember from last time that a rectangular prism will refract the light. It'll come through, it'll get bent a little bit, and it'll come out. But the ray that goes in is parallel to the ray that comes out. I think we have one of those here. It's kind of laid on the side, but the ray that comes in gets refracted and comes out. But the ray that's coming into the prism is parallel to the one that comes out. So it doesn't change the direction of the light if both sides are parallel to each other. Now, in contrast, if it's triangular, it does change the direction of the light. It refracts downwards, and then it refracts downwards some more. It refracts toward the normal first, and then it refracts away from the normal. But because the two sides are not parallel to each other, you wind up with it changing direction like this, sort of like the Dark Side of the Moon album cover. Okay, so if we have both sides parallel, it does not change the direction of the light. If the two sides are not parallel, it does change the direction of the light. Now, if we stack these, a triangular prism over a rectangular prism over an upside down triangular prism, it kind of tends to focus the light. It bends the light downward, doesn't bend the light at all, and then it bends the light upward. And if we smooth out the corners on this, then we get a classic curved converging lens, where if it's designed right, you'll have a focal point, a discrete focal point, where all of the light rays will come together on the other side of the lens. Now, we call these thin lenses. The diagrams we're doing, we're calling them thin lenses, and we're assuming that they're so thin that there's no offset in any of these rays, that they just all do all their refraction right on the very center of the lens, and they all come to a single simple focal point. So on our ray diagram here, let's open this back out and focus again. That's good, and make it go away. There we are. This vertical line is our thin lens. We are going to assume that all of the refraction happens on this one plane, and it doesn't get spread out at all. It just simplifies our process if we do that. So these are very thin lenses. And for a lens, you can send light through in either direction. And there's a focal point on both sides. And the focal point is the same distance from the lens in both cases. Okay, so we're going to look at a ray diagram for thin lenses. And first we're going to look at one where the object is out past the focal point. Let's put it right about here. This will be fine. Okay, here is our object. Now, our We again have three rays that are useful for us. And the first one is going to be a ray which is parallel to the principal axis. So the ray comes from the object, it comes to the thin lens, and because it's parallel to the principal axis, I didn't get that quite parallel to the principal axis. Let's see if I can fix that a little bit. We want this to come out neat. There we are, that's better. Okay. Since it comes to the lens parallel to the principal axis, it will be focused through the focal point on the other side. So that's where it goes. Right? It comes in parallel to the principal axis and is refracted through the focal point. Now, the other one is one that passes through the focal point on the near side of the lens. Here we go. And that one is going to be refracted out parallel to the principal axis. So it's going to do this. There we are. Now, again, this is kind of a reversal. If we have a ray coming in parallel to the principal axis on this side, it's going to be focused through the focal point on that side. And we're just doing that in reverse. So it goes through the focal point and then comes out parallel to the principal axis. And then the third one is actually the simplest one of all. If a ray goes through the exact center of the lens, this is where the sides of the lens are parallel, so it will not be refracted at all. So it will just go straight through the center of the lens, like this. All right. This is like a lens or a prism where the two sides are parallel and a ray will come in, it'll be refracted, and then it will come out parallel. But these two lines are parallel to each other. And if the lens itself is infinitely thin, then there will be no offset between these, and it will just go straight through. And that's what we're assuming with our thin lens. We're assuming that the thickness of the lens is insignificant. Anyway, all of the rays converge over on the other side right here at this point. And it's upside down. But if we were an observer over on this side, and I kind of didn't give myself room, it will appear like all the light is emanating from this point. So our image is upside down, and but it is a real image. It's a real image because all the light actually does pass through this point. It's just flipped upside down. Might also be magnified to some degree too, but it depends on where you set the object. Okay, last one here. Let's do one more thin lens. And this time we are going to set our object between the focal point and the lens. All right, so let's put it right here. Same deal. If a ray comes from the object and comes in parallel to the principal axis, it will be focused through the focal point. Okay, and it'll go out that way. If an object comes through the focal point on this side and then strikes the lens, then it will come out of the lens parallel to the principal axis, like that. And then finally, if a light ray goes through the center, it will continue on without being deflected at all through the center of the lens. Now again, we see these three rays and they're all diverging. So how can you get an image? Well, if you project them backwards, and this third one, surprise, surprise, goes through the same point. All of the rays appear to be coming from this point here. Okay? They appear to be coming from this point right here. So an observer out here, we can put our eyeball out here, who's watching, our observer, all of the light rays seem to be coming from this point right here. So the image is upright and is magnified. And this is how a magnifying glass works. If you guys have played with magnifying glasses, and you can look at your hand with it, and if you put your hand at this point, it makes your hand look bigger back behind the lens. And it depends on how close the object is to the focal point, or how close it is to the magnifying glass, about how big, how much it magnifies. But we wind up with a virtual image, because the light does not actually pass through this point. It just appears to be coming from this point. The light actually goes from the object through the lens and appears to be coming from farther back. So this is a virtual image, but it does magnify. That's it. So we have seen ray diagrams for curved mirrors, where we've moved the object around to different places, and for thin lenses. All right, that's it. Thank you for your time, and we will see you next time.